addition reactions of alkenes. So we've looked at alkanes. Alkanes undergo substitution reactions. Yeah? Either we can substitute a halogen to give us a haloalkane, or using ultraviolet light plus the halogen, or we can have a haloalkane with a nucleophile to go into an alcohol or an amine. Yeah? Alkenes are more reactive, than alkanes. Alkenes are more reactive than alkanes. The reason being is they undergo addition reactions. Notice how one of the differences is that no reaction conditions, right? So in the presence of an alkene with a halogen, no reaction conditions. So we can do this in a dark room, yeah? And the other difference is the product. So if I have ethane and bromine, gives me bromoethane. If I have bromine and ethene, the bromine adds across the double bond. So that goes to there, and that goes to there, and we lose one of those. Okay? So adds across the double bond. Unlike substitution, bromine is added to both sides. That's the key difference. We can also add water, but hydrolysis we would call this, or hydration of ethene. But the reaction conditions are pretty high. We need a phosphoric acid catalyst, H3PO4, and we need to do this at 300 degrees, right? So a better or less energy intensive process is to halogenate our alkane and then do a nucleophilic substitution, because we can do that under standard conditions. If I want to go from the ethene direct to ethanol, 300 degrees, high energy specific. So the water, think of water as being HOH. So the H adds to one side, the OH adds to the other. Yeah? One day I'm going to draw on an actual TV that doesn't have a cover on it. Okay, I'm just going to stick to here for now. Let's consider another example. Draw the structure for propene. Draw the structure for propane. And then we go into addition polymerization. I don't talk too much about polymers at all because it's not really in the course. The only polymers we really talk about is proteins. We don't talk about high density polyethylene or anything like that. Yeah, so that's about the extent of polymers in Year 12. I haven't seen a polymer question in a few years. We should know that it can polymerize with itself by that double bond opening up with the presence of a catalyst to give us a polymer. We can have other polymers form, recognizing the repeating unit and so on. Okay, reactions of alcohols. Thinking back, we've got a primary alcohol, secondary alcohol, and a tertiary alcohol. Remember, that refers to the number of carbons attached to the same carbon as the hydroxyl functional group. Primary alcohol, 1 carbon. So the alcohol sits on a terminating carbon. Secondary alcohol, 2 carbons attached to the same carbon. Tertiary alcohol, 3 carbons attached to the same carbon. And so these react differently. Note that even though I've got this branch coming here, right, that's still a primary oxidation of alcohols. We know we can combust alcohols. We've seen that in fuels, particularly with bioethanol. The way in which alcohols oxidize is different from one to another. A primary alcohol, when you oxidize it, goes to a carboxylic acid. So Cr2O7 2- is dichromate. Dichromate is a strong oxidizing agent. An alternative strong oxidizing agent is permanganate, MnO4-. In both cases, they are acidified. So acidified dichromate or acidified permanganate. Potassium doesn't do anything. Yeah? So the oxidizing agent will actually reduce, and so we could consider this, and there are some questions on the previous exams where it asks you to do the half equation for the reduction of the dichromate or the reduction of the permanganate. I won't get you to do that today. So the product, again, of the primary alcohol being oxidized is carboxylic acid, but it goes via an aldehyde intermediate. And we can actually reduce this, we can extract this in as part of the process. But what I want you to think, primary alcohol goes to carboxylic acid. Secondary alcohol, because the secondary alcohol is not on a terminating carbon, it can't go to a carboxylic acid. So when a secondary alcohol is oxidized, imagine that this bond, essentially what happens is that bond goes to there and that pops off. So oxidation of secondary alcohol produces a ketone. And if you were to have a guess at what is the product of a tertiary alcohol? Nothing. Yeah? Tertiary alcohols will not oxidize under standard conditions. Right, because I can't say cross this off, because then I end up with 5 bonds around that carbon. So if we think about it from a space filling model, we can't oxidize this further because, right, there's strain there. It's bulk, we've got all these branches coming off. I can't access that carbon center very readily. So if we want to think about synthesis, we've got to think about access to particular points in which a reaction or rearrangement of bonds will occur. Esterification. Hopefully this isn't anything new. We looked at this last year. Take an alcohol, take a carboxylic acid, condensation reaction or esterification is a subset of condensation. Condensation is the formation of bonds. Hydrolysis is the breaking of bonds. So we're forming a bond using, typically what we use is actually H2SO4, liquid or concentrated H2SO4. Yeah? Not just any acid. It needs to be concentrated. Yeah, the reason, so it's concentrated to the point in which we list it as liquid, and that's really important. Yeah? Reaction conditions are important. So when I make an ester, concentrated or liquid sulfuric acid. So we're talking 10 molar, 12 molar, very, very strong. Because we're using this as a dehydrating agent. Yeah? Esters are prone to hydrolysis. They're prone for this bond to break again back to their substituent particles. Don't forget the water. Yeah? Condensation reaction, water as a product. I'm not entirely sure which oxygen goes off to give the water. I like to think of it as this one, right? So then in my thinking for naming of my ester, I know that this single bond oxygen comes from that alcohol portion. Naming of esters, which we've seen before, we go from the alcohol portion, identifying which side that is. So in this case, ethyl ethanoate. And like I had in that first question, or that last question on the board, is be wary of the position of the C double bond O. Find where that is, draw a line. Where the double bond O is our carboxyl portion of the molecule. The single bond oxygen is our hydroxyl or alcohol portion. And note, the C double bond O, the carbon as part of that, is part of the counting. We can actually form a polyester. Again, not too concerned about polyesters. Polyamides, yes, we'll get to that when we get to proteins. So we can combine all these ideas together. If we start with an alkane, we can add chlorine gas. What's the reaction conditions for that required? UV or heat, yeah? We must have that present. So in this example, we've got ethane, UV or heat. One of those hydrogens is substituted with a chlorine to give us chloroethane. We can form that from an alkene even. If we go ethene and add hydrogen chloride gas, hydrogen and the chloride add across the double bond to give us the same product, right? So there's multiple ways in which we can make molecules. We can take our chloroethane, use a nucleophile, strong base, chlorine, leaving group, leaves off, replaces with a hydroxyl group to give us an alcohol. We can then take our alcohol, right, oxidize it to give us our carboxylic acid. Then we can take a carboxylic acid and a different alcohol, or some of the same alcohol if we want ethyl ethanoate, for example, or if we want a different alcohol portion, add those two together with liquid, concentrated sulfuric acid, to give us our ester. Yeah? That makes sense? Name that structure. What do you reckon? Should take you probably 10 seconds. Ethyl propanoate is correct. Here we go. All right. Synthetic pathways from alkane or alkene starting reagent for the production of ethyl propanoate. Step 1, make some ethanol. So if we want to start with ethene, I'm going to add HCl to give us chloroethene, ethane, and then use my nucleophile to give us that. Or I could have gone straight from here to here using water, 300 degrees, and a catalyst, H3PO4. Which is here. So H3PO4. So two alternatives, to make ethanol from ethene. Then I want to make propanoic acid from, say, propane. Start with my propane, halogen substitution to give chloropropane. Right, we're not worried about 2-chloropropane because we're not going to have branched esters. So we're just determining hydrogen there. Nucleophilic substitution to give us propanol. Oxidize the propanol to give us propanoic acid. So now I've got ethanol from ethene. I've got propanoic acid from propane. I combine them together using sulfuric acid, concentrated, and I get my ethyl propanoate and water. Yeah, so there's a lot of ideas here because there's not just one reaction. There's about 5, isn't there? So it's combining all these ideas together. And there's in one flowchart. Yeah, so starting with our starting components, different reactions going together to give us our final product. Okay, and let's go